systems where we take linear actuators and put them together to make multi-axis systems. Festo likes to use the term handling system. Sometimes you'll hear them referred to as Cartesian systems. You might even hear them referred to as linear robots or Cartesian robots due to some areas where they overlap with other types of industrial robots. But we prefer to think of them just as positioning systems. Anytime you need to position something in one or more axes, a Cartesian system like this may be a really good solution for you. Now, the key components of a multi-axis system, I'll start by showing this image of a 3D gantry. You'll see the three principal axes of motion. Oh, sir, you can grab that chair right there if you'd like, right next to Matt. Yeah. And if you wouldn't mind standing, I would love it, because then this would be my first ever standing room only event. And I really want to check that box. Thank you. So we've got the three principal axes of motion, X, Y, and Z. And then each of those aligns with one or more electric actuators. In this system, which we call a gantry, 3D gantry, we've got a primary X-axis and a secondary X-axis. They are connected with a connecting shaft that rigidly couples those two axes together so that the Y-axis, which is spanning across there, moves very precisely over the full stroke. This is why we call these a gantry, 3D gantry, or even sometimes a gantry robot. And then the Z-axis, of course, is attached to the Y. Of course, all of these will be driven by a servo motor. So we'll have an X-axis, Y-axis, and Z-axis servo motor. Servo drives are not shown in this picture. The servo motors may or may not be connected to the actuators with gearboxes, just depending on what type of motion we need. But we'll use planetary gearbox if we need to have that mechanical advantage. Also shown here is the cable management. Every axis has energy chain integrated into it, as well as all the bracketry to support that energy chain and attach it to the mechanical axis, which is not trivial. If you've ever designed energy chain into a system, there's a lot of mechanical work that goes into designing that in. This comes from Festo as a catalog item, part of the standard product, everything that you see there. Adjustable mounts also come as part of the solution. These mounts make it so that you can mount the gantry onto the machine frame, make sure that everything's aligned and parallel. There's no roll in the X-axis. This will increase the lifetime of the gantry. So a 3-axis gantry like this is 3 degrees of freedom. Oh, the adjustment, they will do 3. They'll do roll, pitch, and yaw, I think. Yeah, there's adjustability for all 3. These types of systems are used in a wide range of applications. A couple of videos here showing the one on the left is a type of palletizer. Pick and place is a very common application for any type of robot, but Cartesian systems in as well. On the right, we're showing a liquid handling system where we're picking up vials of liquid, presenting them to a camera, and then moving them into different areas for some type of lab automation test. This video will show a real palletizer in action. There's a few things to note about this. First of all, it's a fairly large workspace. Plenty of room to move a full pallet of cartons in and out of the space. You'll notice that the gantry sits above the workspace. This is indicative of a Cartesian system. They generally sit above the workspace. This frees up a lot of space on the ground because the gantry system, basically, its footprint is equal to the workspace footprint. You'll see that there's quite a bit of robust tooling on the end of the Z-axis as well. There's an array of suction cups. All the vacuum generators for those suction cups are on that tooling, as well as the flow sensors for that. And all of the tubing, sensor cables, et cetera, for that tooling is going through the cable management along with the servo motor cables. This is a little bit simpler system. This is what we call a linear 2D gantry, or a YZ. We've got one horizontal axis that's fixed to the machine frame, and then one Z-axis. At the end of the Z-axis, we have a rotary module, and then an array of suction cups. We're basically picking up, I don't know what exactly this factory is doing, but Those plastic trays, we're picking them up after they've been formed, and we're putting them in stacks for some downstream process. Couple of things to note. We're not using Festo motors here. This is something we do for a lot of our customers. We provide the end plates for you to mount whatever motors you're using. Although in a lot of the videos, you're going to see Festo motors on the system. Typical application, as you can imagine, is part feeding, is material handling, basic material handling. In this machine, this is a lab automation machine. You can see here the operator opens the door, and then we'll add samples into the machine. There are actually two linear systems here, two mechanical systems. One that is handling the trays full of vials. That's the one you see moving right now across the screen. And then there's a second one down on the floor that is this one right here. This is aspirating and dispensing solutions into the small vials for the actual test to take place. You'll notice that the Cartesian system, again, is basically the footprint is equal to the machine footprint. This is an area where this type of system works really well. We can basically make the stroke lengths of all the different axes exactly match what's needed by the workspace. You can imagine if we were to do this with a 6-axis or a Scara robot, we'd have to change the floor plan a little bit, maybe carve out some space to put the robot, and maybe change the overall size of the machine. This video is showing another type of benchtop equipment. This one is an automated test cell. A little bit older video. I think that's a Windows phone there, but all the hardware shown there on a Nokia device. All the hardware there is still readily available today. This particular XY system is a very low profile system, and so it's very popular with benchtop equipment, both in electronics and life sciences. And to it, we mount a conventional electromechanical ball screw axis, which you can see moving up and down there. And then what I think is kind of interesting about this one is on the linear axis, the vertical axis, we've attached a second pneumatic axis, which is acting like the finger pushing the buttons. You can see there's some customer has some of their own and tooling on the end of the pneumatic axis as well. We also do some material handling for machining centers. This one is another type of another flavor of that 2D gantry. So we have one horizontal axis that's fixed, and then two vertical axes attached to the horizontal. Each one is outfitted with a fairly heavy-duty pneumatic gripper. This is so that we can load a fresh part and take out a machine part all in one cycle. That's why we have two grippers. You can see there's cutting fluid all over the place. Everything is spec'd in so that it's not a problem. You get a good look at the cable management there. All the tubing and sensor cables for that fairly robust end of arm tooling is routed up through that energy chain and out of the way. And then one more video I'd like to show is this is an automotive supplier. You'll see the operator load some parts, some part of an interior of a vehicle, and then the gantry takes over and automatically places these plastic stakes into the part. This is another example where the axes of the gantry are defined specifically to the size of the part. This part is very long and narrow, and so we have very short x-axes, a fairly long y-axis. And the footprint of the machine is not that much larger than the part itself. This is a strength of Cartesian systems. Another strength is that it's impossible for them to move outside of their workspace. So guarding is very straightforward with a Cartesian system. Go ahead.
So you mentioned a couple of times that you built the Cartesian system to fit the envelope of the equipment.
Yep.
Are you suggesting that these are standard lengths that are put together, or are these custom length built to
custom
the millimeter?
Yeah. Yeah, the question is how fine can we go with the stroke length of the different axes? With a belt actuator, we can go down to the millimeter. Our standard catalog, the longest we go is up to 3.5 meters on the x-axis. Ball screws, typically we go in increments of 100 millimeters, just for speed to market. Rather than machine ball screws to a millimeter length, we stock a lot of our inventory. We have ball screws ready to go so that we can be quicker to market. So typically ball screws will be in increments of 100.
So most of the stuff is built to order, not like stocked on a.
It depends on the type of axis again. So the ball screw axes, a lot of times will be stocked, but belt actuators are built to order in Mason, Ohio. Yeah, thanks for the questions. Okay, talk a little bit more about modularity and configurability and what you get from Festo. This system here is what we call a 1D. It's a single axis, so not multi-axis, but this is where we start. You can see here we've got a belt drive actuator. There's a gearbox connected to it, servo motor, and of course the cable management. I mentioned earlier, if anybody designed energy chain into an axis before, takes a fair amount of work, right? A lot of brackets and things to attend to. Everything you see in this picture is a catalog item. So this comes out of our tool, all the bracketry designed to the correct length, ready to accommodate your motor cables, your sensor cables, and any tubing that you need for your end of arm tool. After the 1D, we go to what we call a 2D linear gantry. This is, I've referred to it as a YZ. So essentially the same as the 1D, but now we've added a Z-axis to the horizontal axis. And in this way, we can start to see how a lot of people refer to this system as kind of like building with Lego, because that's what we do. I mean, in a nutshell, with these standard systems, is we're taking catalog items and building on top of them to make multi-axis systems. The next system is what we call a 2D surface or flat gantry. This is basically a 3D gantry without the Z-axis. So if you have any special tooling that you want to mount to the gantry, say you have the one example that I think of is some automated screwdriver that has both the spindle for the screwdriver and the linear motion built into a single head. You can attach that right to our Y-axis carriage, to that robust mounting plate, and you don't need a Z-axis from us.
Another question.
Yeah, go ahead.
You go back one.
Yeah.
Are those blocks hanging off the bottom for mounting to like 80/20?
Yeah. The question is about those mounting blocks. So this particular system is designed to be mounted to like a vertical surface, like a machine frame or a wall. Those are adjustable mounting feet. So those allow us to align the axis very precisely. Yeah, just for mounting.
Just on the bottom.
No, there is one on the top that you can't see. So there's an it's like a 4 or 5 part piece. There's an aluminum plate that clamps to the body of the actuator. And then those, that little wing there's one on the bottom and one on the top. Those attached to the machine frame. And then you have adjustments on top and bottom.
So for steel,
yeah,
drill these holes and are precise.
This will allow you to accommodate for that. Exactly. Yeah. And then it's kind of a similar situation on the horizontal ones. These are actually what we call profile mounts. These are very simple. These require a little bit more precision in your machining on your machine frame, but we have adjustable mounts that you asked about earlier that give you that adjustability in multiple dimensions. So your machine frame doesn't have to be quite as accurate. Then the 3D gantry, which we've talked about a little bit already, many different variants of this. And finally, the 3D cantilever, which is just like the 3D gantry, except we've gotten rid of that secondary x-axis. And there's some benefits to this. For one, cost goes down because you're using less hardware. Another one is if you're in an area of the machine where you want to have an operator needs to have access, getting rid of that secondary x-axis can free up that space. But there's some downsides too, or some trade-offs, I would say. You can't have as long of a y-axis because you're not supporting that other end. So generally, the workspaces allowed with a cantilever system are going to be a little bit smaller or significantly smaller than a 3D gantry. But the main point here is that you can get all of this from Festo fully assembled. The multi-axis mechanics, the servo motors and drives, gearboxes, all the hardware to mount everything together, the brackets to hold everything, cable management, your sensors, even the mounting feet, all under a single part number. This is I want to talk a little bit more about the modular or the configurability of these systems. This is a 2D gantry, XY, looking at it from above. That blue box is basically the workspace of it. This particular system that I designed earlier this week in our tool, it has a 500 millimeter in X by 300 millimeter in Y. That is the workspace of it. If we wanted to stretch the y-axis out, we can do that very easily. For example, we could easily go from maintain 500 in the x and go 1500 millimeters in the y, just by changing some parameters in the design tool. We can also do this in the x-axis. I've shown this system 2 meters in the x and 300 millimeters in the y. I actually originally was going to show 3.5 meters, but it looked so ridiculous on the slide that I pulled it off. You couldn't really see it. And then, of course, we could expand in both directions and have something like a 2 meter by 1.5 meter workspace. The key that I want to show here is that the size of the actuators doesn't change in all of these systems. Each of these systems is designed for the same payload. With a Cartesian system, you decouple payload from reach or workspace. And I feel like this is an important distinction from other types of industrial robots. As your reach increases, you generally get more payload. So sometimes you're paying for capacity that you don't need. With a Cartesian system, you can specify the payload and the stroke length all independently from each other. And so you're only paying for what you need for the application. Yeah, go ahead.
So you get for the amount of price, because each axis is linear, right? So
yeah.
Do you get like area becomes exponentially less expensive? I haven't thought about it.
I have never thought about it in that way. So the question is, yeah. No, yeah, I see what you're saying. So as the workspace increases, the price will increase, but it's not linearly, right? Because in all of these, the servo motor is the same, the gearbox is the same. Everything just grows a little bit, but not on the most expensive parts. So yeah, your price increase is probably doing something like this. Yeah, I don't know if it's truly exponential, but you know, it is going up, but it's not going up linearly. It's tapering off. Good question. I've never been asked that before, but yeah, go ahead.
With that increase in stroke length, we'll say, do you see loss of precision at all?
No, thank you for pointing that out. That's actually one of the benefits of a gantry system like this. Wherever we are in that blue square, the repeatability is the same. So a typical gantry like this will have a repeatability of plus minus 0.1 to 0.15 millimeter. It doesn't matter where you are in that workspace, it will always be that. Yeah, this system is belt on the X and the Y. And then the Z could be belt or ball screw. On some of the other systems, we can do ball screw on all 3 axes. So you get better repeatability on the ball screw. So on a fully ball screw system, I would say you'd be less than plus minus 1 millimeter, but I don't want to go too far in that area. We always specify our systems at 0.1 or 0.15. So I'd prefer to stick to that. Yep. Yeah.
Ball screw is different.
Well, ball screw is generally more precise, but we are stacking some of the intolerances. So when you get to a 2 or 3 axis system, I don't know. I've never seen one of our ball screw systems less than plus minus 0.1 millimeter. So I'm going to stick with that.
That accuracy.
Repeatability. We talked a little bit about rotary, adding rotary to the Z. The main way we do that is with what we call a rotary module. These can be pneumatic, where we have basically 180 degrees of rotation, maybe a little bit more, or We can go less than 180 degrees, or in this case, it's an electromechanical rotary module where we're driving it with a servo motor, and then we have indefinite or infinite rotation in either direction. These rotary modules are designed to fit directly to the end of the z-axis with no interface plates. If most of them, if an interface plate is required, it's generally going to be a catalog item that you can order. Some of the rotary modules are also designed with feed-throughs, so your sensor cables and pneumatic tubing can come right through the center without any additional modification. And then to that end of arm or that rotary module is typically where you're installing your end of arm tooling. So your grippers, your suction cups, what have you. And for Festo grippers, for example, our pneumatic and electric grippers, you're typically we often have a catalog adapter plate that will mount that gripper directly to the rotary module or to the end of the z-axis. So again, you don't have to design or machine anything. Some examples of end of arm tooling. This video shows one of our more specialty tools. This is a combination module. It's actually on the demo that we have by our table out back. It's a combination module that was developed by our Life Tech team. They focus on the life sciences industries. This module has a little bit of vertical or linear motion. It has a rotary for capping and uncapping the vials, and then it has little grippers to grab the cap of the vial. So all that is available as one part. But also in this video, you see some other grippers grabbing the vials and some other forms of or other instances of electromechanical actuation. These videos show one of our pneumatic rotary modules. The video on the right is showing basic principle of operation. The video on the left is showing it in a conceptual application, kind of a clever way to use it, I think, to do basically like a tool change. It's rotating between two pneumatic grippers, and it is attached to the end of a pneumatic linear actuator. And then that pneumatic linear actuator on the Z is then controlled by belt drive on the horizontal axis. It hopefully becomes clear at this point that Festo is primarily known as a pneumatic company. We have a wide range of pneumatic components. Generally, they all work very, very well with our electromechanical systems too. And then this video shows another type of more intricate end of arm tooling. We have an electromechanical horizontal axis, and the tooling on there actually has 3 pneumatic actuators. It has 2 rotary and a linear. The first rotary is pivoting that linear from vertical to horizontal. And then the second rotary, after we pick up a part, is rotating the part like a wrist almost. And then suction cup down at the bottom. All of the air for that tooling, both the positive pressure air and the negative pressure air for the suction cup, is being driven by that Festo valve manifold at the top of the tooling. That single manifold is able to provide both positive pressure and negative pressure for all the actuators on that tool. And then all that tubing is going up through the energy chain and out to your valve manifold or your control cabinet. I take that back. Tubing is going to the valve manifold. The supply tubing is going through the energy chain back to your air prep. How do you get started with handling systems? If you've never used Festo or another manufacturer for these things, I think a lot of you are familiar with designing by hand based on the people that raised hands before. I think you know that this can be time consuming. We estimate for some of these larger systems, it could take anywhere from a week to 6 weeks to design it completely from scratch when you have nothing defined on a 3 or 4 axis gantry. So that will depend on your project requirements, your system complexity, of course, your engineering experience, who's doing the design work. The other option is to use a proven design tool. The Handling Guide Online is the tool that we offer to start you on this path with everything you've seen so far. It's completely designed by Festo. It's more than 10 years old. It's built on over 2 decades of developing handling systems like this for our customers. You could do 1D, 2D, and 3D systems. It's very accurate and fast. Not only do you dimension or size the system, but once you've selected it, then you can configure it without the options that you want for your application. And you're going to be able to reduce your design time from weeks to hours, reduce risk, reduce your errors, and just basically streamline your process. One of the pieces of feedback we get about machine designers that start to use this tool is how quickly they can iterate on their designs, how quickly you can go from concept to quote and then iterate on that over and over, and all trust that you're going to get everything under a single part number and get the CAD file. You'll see in a minute the CAD file is available basically instantly once you've built the system.
What are the price ranges for this?
Oh, it depends on complexity. I would say the smallest gantries, you're talking about a few $1,000s, and then up from there, depending on the size and the payload. And Handling Guide Online handles up to 3.5 meters in the X, 1.8 meters in the Y, and 2 meters in the Z, and up to about 50 kilograms payload. After that, we go to our customer solutions group, which I'll talk a little bit more about in a minute. But the tool itself handles that range. So how the tool works is it's very simple. It's like any type of like wizard-based sizing tool or online tool. You start off by selecting your system type, 1D, 2D, or 3D. Then you enter your application details. What is your workspace? What is your payload? What are your cycle time requirements? Are there any additional forces on the Z, etc.? And then you immediately get a list of results. And those results will be listed in order of ascending price. So it's kind of like good, better, best. Typically, every system in there will be sized according to your application. But for example, a lot of times we'll see as the first option a system with step motors. Step motors are great. I love step motors. I've worked with them my entire career, but not everybody loves them. And so once you go past that, you'll typically then get into the servo motors. And then from there, you'll get into larger systems that are a little bit oversized for your application requirements. But we do see that sometimes customers have a preference in their vertical axis or the type of horizontal axis that they want to use. And so they'll skip past those less expensive systems and go with something a little bit more to their liking. Anyway, this results page gives you a bunch of information to compare the different results. You select one, and then you move to configuration. And here you set your motors and drives, or deselect them if you're going to use third-party motors. You define your proc sensors or end of travel, add any tubing, specify your cable lengths, and then select how you want it assembled. Do you want a full assembly from Festo, which means that we fully assemble the gantry, we route all the cables, and we do a functional test, all for you in Mason, Ohio, before we create it and ship it. If you choose partial assembly, we build all the individual axes with energy chain, with sensors, with mounting feet, everything that you need to easily assemble it in the field. We just won't route the energy chain or do that functional test of the completely assembled gantry. But you save a little money on the trade-off. Another use case where you might use partial assembly is I've seen instances where you have to kind of shoehorn the system into an already defined machine frame. This is an advantage also of Cartesian systems. They are often, because of the way that their workspace, the way that they're so close, their dimensions are so close to the workspace, we often see them kind of nestled in amongst a lot of other automation, like surrounded by other actuators and other processes. You'll often see them kind of buried inside a machine because they can be so compact. And then you get your complete solution. Once you've configured it, then I'll zoom in a little bit here. First thing you'll get is an CAD preview in line with the solution. So your CAD file for your system is already generated. You can take a look at it here in that preview. And of course, you can download the CAD file. And I've yet to see a software that we don't support. I'm not a CAD designer, but nobody's ever said, oh, I wish you had this format. I always download STEP because I use a free online STEP viewer, but there's just a ton of them. You get the all-important system ID. This is your single part number that defines not only the solution that you've selected and configured, but all of your application information. So if you copy and paste this and email this to a colleague or a Festo rep or a Mechatronic Solutions, your salesperson, and say, here's the system I want, they will be able to see everything that you put in there. They can review your choices, they can quote it for you, etc. That system ID is the key to unlocking all that. It's also your key to getting spare parts. If anything gets damaged or needs to be replaced in the future, this is something that I don't have time to show you today, but I'd love to show you. You could put this into the Festo website and get an exploded view of all the parts in the system, and you can order replacement parts. Of course, you can get price and delivery, and the very important technical data sheet. This is a PDF that has all the information that you entered in your application. It has all the bill of materials for everything in the system, and it also has performance data of the servo motors. For example, you get your continuous torque and peak torque and the frame size and the rotor inertia of the servo motor. So I always tell people, look, even if you're not planning on doing Festo motors, you should do one sizing with Festo motors, because the data sheet is going to give you all the information you need to cross that over to your vendor of choice. Frame size, rotor inertia, continuous torque, peak torque, rated power, etc. Really handy for a lot of different use cases, that technical data sheet. And then finally, you get the commissioning file. If you are using Festo motors and drives, well, anybody's drives for that matter, you get this beautiful mechanical system in, and then you get a handful of servo drives that you now got to connect, wire up, and program. With Festo drives, we offer a commissioning file. And what this file contains is all the application information that you entered. So it has the stroke length of the actuators. It has the ratio of the gearbox, if there was a gearbox included. It has the motor information. It also has your payload information, all in the commissioning file. So you download that commissioning file to your X-axis servo motor. There's one for the Y-axis, one for the Z-axis. And within minutes, you're up and running. You're homing the axis. You're doing some test moves from within the software. You're ready to go. Hand it over to your controls engineer, and they can start programming very, very quickly, all due to this commissioning file. And this is something that we added in the last, I think, couple of years, but it's an amazing feature for anybody using Festo drives. A lot of times people will ask me, okay, I like what I see in Handling Guide Online, but I need something a little bit different. This is where we get into our customer solutions group. This is our value-added engineering group. They're based in Ohio. We also have a group in Ontario, Canada, and one in Mexico. Basically, these guys design everything from very simple systems to very complex systems. They will use standard Festo catalog items. They will use custom things that they design from scratch, and they will use third-party components when necessary or whenever it meets your requirements. And one of the things they really do well at is more challenging multi-axis applications. So this video is actually showing some of the guys in the Ontario facility creating up various electric actuators that they're getting ready to ship. I think that last clip there was of a partial assembly of a gantry. What I tell people is anything outside of HGO or anything beyond what the online tool can do, our customer service or customer solutions team can do. And I'll show you a couple examples of that. This is a very large gantry that our customer solutions team did. This is our facility in New York. The dimensions of this system by itself are already a little bit outside of HGO. I think that Y-axis span is well over 1.8 meters. It's also a very long Z-axis. So the dimensions itself take it outside of the Handling Guide Online. But also there's a special, we've attached the rotary module, and to that rotary module, a special suction cup gripper thing. And then the last piece that we offer as part of the solution is the conveyor tracking. So we use Codesys and soft motion in all of our PLCs, and we can do conveyor tracking. And so there's a camera at the front end of the conveyor that takes a picture, notes the location on the conveyor, and then we track it, pick it up, and drop it off. This is another customer solutions output. This one I had to look at for a little while. Basically what's happening is it's got two parallel X-axes that are fairly short stroke on the bottom. There's a connecting shaft along the back, so one motor driving those two x-axes. And then they built this framing and took like another set of parallel axes with connecting shaft and tilted them up and mounted it on there. So what you see on the ends are these, the top half of the Z, those are synchronized with that connecting shaft and that one servo motor. And then on the actuator itself, we have the option, standard option, to add a second carriage, a carriage that just floats. So on that carriage, they attached a rod style ball screw actuator next to it. So on that one linear bearing rail, you've got two independently moving carriages. Kind of a clever thing. I don't know what the end use for this